Buongiorno, you brave souls who are still listening my lectures. So today I will be speaking about combination of lenses, especially in the setting that we want to image now using several lenses. And this is actually a problem that is very important because many optical instruments actually behave this way, so that we actually have many optical instruments that are formed out of using several lenses. And why this is the case is that that really helps us to kind of, for example, help with aberrations, so that if you put many lenses together in a proper way, you can actually reduce the aberrations quite dramatically using these kind of triplets and doublet lenses. So that's one thing that I can straight on mention to you. And this is basically the kind of motivation for this lecture. So what I will be doing, I will be generalizing the treatment to many lenses. So basically, in a nutshell, we will first consider how a first lens behaves, what kind of image will be formed and where, and then we will use that formed image as our object for the second lens, and then solve the imaging problem of the second lens and so forth. And if we would have a third lens, then of course we would be solving subsequently, like then using the object point of the third lens, the image of my second lens and so forth. So basically one component at a time. And then at the end of the lecture, once we have solved this situation, I will be saying a little bit about the kind of practical considerations when we are dealing with several lenses, so that in case you need to understand things more carefully, then what would be the directions that you should be starting your own journey. So hopefully I can clarify a little bit why many lenses are actually a kind of very relevant topic in optics and photonics. So combination of lenses. So I will now start our common learning journey of learning. So let's see, we are considering lens systems, and when we are looking at real optical instruments, basically many of them actually consist of several lenses. The kind of main motivations and kind of benefits that we get of actually using many lenses would be mainly the reduction of aberrations, especially the reduction of chromatic aberration that can be very easily understood by making a doublet lens and a triplet lens. So basically a lens system consisting of 2 or 3 slightly different types of lenses, and that will be solved in the future courses. And then improvement of performance. So we can, for example, increase the amount of light that we are collecting while we are still keeping the amount of aberrations reasonable. So that's also something that we could do by just having several lenses in our optical instrumentation. So this is something, and we could, for example, then also have some kind of apertures and stops in our instrumentation that could be used to control in a continuous manner the amount of light that is actually going through the system. So that would be also something that we could quite easily take into account and manage when we have a system consisting of several lenses. But here I would be pointing out that please note reduction of aberrations. That's the kind of key here. And that's the kind of main motivation. So we really want to understand how a system of lenses behaves. And here, as I said, the treatment will be made one lens at a time. So that's the kind of crucial point to remember here. And then we start with the lens that is first illuminated with the incident light, and then we will solve the imaging problem of that. And then we will use the subsequent image as our object for the second lens and so forth. And here, for simplicity, let's only consider the simplest possible scenario, and that would be 2 thin lenses that are separated by a distance of d, and then they will have focal lengths of f1 and f2 subsequently. So this is the kind of easiest scenario I can imagine, and that kind of shows you the point. And of course, you can do it yourself by just adding a third lens into the system and what happens and whatnot. By the way, another thing that is so nice when we are dealing with several lenses is that then we can also have now, for example, the focal length as a variable parameter if we can adjust the separation of the lenses. But more on that later, I hope I can remember. So we can actually also make just zoom lenses where we are actually by adjusting the lens positions, but not adjusting the material composition of the lens and not really the focal length. So we are not touching, for example, the curvature of the lens, but only the separation D. We can then adjust the total magnification of our imaging system. So essentially the effective focal length. So this would be another thing that we can easily achieve when we are actually using a combination of lenses instead of a single lens. So we can have parameters that now start varying with respect to some parameter that we can easily control in experiments. For example, the separation, we can just have a lens in a translation stage, and that's it. That gives us a tools to kind of adjust, for example, the focal length. So let's now consider the two lenses illustrated in the figure in the below. We have an object distance, and let's denote that distance now as an SOI. So that's the distance of my object point from the first lens, and the height subsequently we consider an off-axis point. So the height will be YO1 from the optical axis. And the image now will be formed after the first lens into the point of SI1. So that would be the image location with respect to the first principal plane of my first lens. And then this will be equal to, looking at the figure, D minus SO2. So essentially, like as usual, we have a object point here at a distance of YO1 from the optical axis. The separation between the object and the first principal plane of my lens is SO1, and then an image will be formed here denoted with the YI1, and this is now the separation of my image point from the optical axis. And here the image location SI1 is essentially, looking at the figure, D minus SO2 parameter, giving us my now separation of my object point from the second lens. Once we start considering the kind of imaging using the image process using the second lens. So the first image acts as the object of my second lens, and this is now how we can understand the image formation process for the second lens. And this implies, of course, that the YI1 equals to YO2. So this is what we see by just looking at the figure. So the kind of size of my image after the first lens, this YI1, this by definition, since we take this image to be our object, then the distance from the optical axis of this point will be, of course, the same. And now let's look things further. We can also consider the magnification of the system, and that we can easily do by just direct calculation. So let's define that the transverse magnification of my now combination of lenses. Let's define that's the kind of ratio of my image length, the separation from my image point from the optical axis YI2 with respect to the distance of my object point from the optical axis YO1. So this is basically using the same definition as before for the transverse magnification. What I can do is that I can multiply and divide both of these terms with the YI1. So basically I'm just adding into this ratio on denominator, and on denominator YI1, and I get these kind of two ratios out. And why do we care? Of course, we can rearrange things. So then we can see that we actually have two ratios. And this, remembering the previous lecture or just the definition of the transverse magnification, this is essentially the transverse magnification of my first lens. So essentially what is the size of this arrow? What is the length of that arrow with respect to the length of this arrow? So that gives the magnification of my first lens. And similarly, the same ratio that gives the transverse magnification of my second lens. And I can now verify that the total magnification MT of my combination of lenses, a lens system, is equal to the multiplication of the transverse magnification of the first lens, MT1, times MT2, the transverse magnification of my second lens. And this is super nice because we can easily now calculate the system's total transverse magnification. What is not as easy is that how do we calculate the final image location, SI2, and this is actually that we need to brute force solve the system one lens at a time, and that's it. So we cannot easily calculate things as was the case with the transverse magnification. But nevertheless, this is perfectly doable. We have the lens equation, and we just progress in steps. So we first consider the lens equation for the first lens. So that's of course known 1 over S1 plus 1 over Si1 equal to the 1 over F1. So that was the focal length of my first lens. And similarly for the second lens, we take use of the lens equation. So we have these kind of two equations. And how do we solve this system completely? That will be done as a homework assignment, but we can still consider a special case to kind of show you what will be the kind of outcome at the case where the lenses are close to each other. So essentially when the distance between the lenses is approaching 0. In this picture, of course, it looks impossible that we can put the lenses together, but once we start imagining that we actually have for example, several centimeter sized lenses that are quite thin, most of the time the approximation is valid, so that the D in effect can be quite small with respect to the actual focal lengths of the lenses. So this approximation, even though it's never strictly valid, most of the time it's actually pretty good when we put lenses together. And of course, we could imagine that we would even have the curvatures correct. So I could, for example, have a plano convex lens here. I would have a curved surface on this side, and then a planar surface on this side. And I could have similarly a plano convex lens here, but now this would be a planar side. And then with these two planar sides, I could more easily join the lenses together. And if you want to be actually more careful, you could even glue lenses together by ensuring that the radius of curvature of this side of the lens, of the first lens, equals to the radius of curvature of this side. I could even put them side by side and even glue them together very nicely. And there's something in between. Of course, the radius of curvature could be just freely changing parameters, and we would just put lenses close together, close to each other, and most of the time this approximation is pretty okay. So these are the two lens equations, and I can solve them. So we can really easily solve them for the case when we have the D approaching 0. So we have the first lens equation, and we can then start progressing on this one. So I can write that the SI1 is essentially equal to the D minus SO2. This is what we looked and verified from the figure a few slides backwards. And now if D equals to 0, then SI1 must be minus SO2. And then I can plug that into here, and I will get a similar kind of equation out like in before. And now I can actually write this SO2 using the lens equation of my second lens. So I can solve the second lens equation with respect to the inverse of SO2. So that will be equal to this. So basically I'm taking this lens equation, solving that with respect to this, and I'm plugging this guy into here, and I can then solve things further. So I will have this kind of equality now. And now I'm essentially done, and that was why I said that this is nice and this is a good thing to show in a lecture, and maybe it's better to consider the full case as a homework. We can redefine what is the meaning of SO1. Since we have a lens system, we can just write that will be my SO, that will be the distance from my object point from the first lens's principal plane. And then I can write that this SI2 is essentially the SI here, and that will be it. And then I can write basically a lens equation for the whole lens system by just using these more familiar parameters SO and SI here. And then I have an effective focal length here. So 1 over F would be equal to 1 over F1 plus 1 over F2. So that the effective focal length of the system now is seen to be basically this. And with using this notation, I can write the kind of combination of lenses for the case of D equals 0, similarly just as a single lens equation. And this is nice. Why? Well, this very instantly gives us, when we are using the kind of concept of lens powers, D, which was the inverse of F, basically that the power of the lens is basically the sum of the power of the first lens and the power of the second lens. So I can now quite easily see that if I take two lenses, I put them together, the power of the lens is basically the sum of these two powers of the lenses. And this is quite nice because it's not as easy to see what happens for the effective focal length when we have this inverse relation. So that this is something, at least my mind is not very easy of kind of understanding how these will be affected when I'm changing the focal length of my lenses. But with the concept of lens power, it's more easily to understand what actually happens when I am having, for example, a doublet lens or a triplet lens. So that kind of helps at least me out when I'm trying to kind of intuitively understand how lens systems work out when we are putting lenses like next to each other when the D approaches 0. And the full case will be done as a homework, I think, where we are kind of considering how we make a zoom lens so that if you change the D parameter, we can actually affect the effective focal length. Because in the previous one, that was basically just the lens power summed, so that the D parameter didn't really affect the lens power. But if you really consider the full case, then we can actually have a variable focal length out from my lens system, and that is nice. So what we can do in general when we have 2 or more lenses is that then we can, for example, have a system that we have a variable focal length. So basically we are changing the lens power. So this is nice. We can, for example, use that to make a zoom lens with an SLR camera. And perhaps from the kind of more general point of view, even more useful system is that if we are now making lenses using 2 different materials, and especially when the refractive index profiles have a different kind of dispersion, so basically their wavelength dependence is different, then we can really reduce aberrations dramatically by just designing proper lenses. So especially we can designing lens doublets and triplets that can be used to minimize chromatic aberrations. And this is super nice because then these kind of lenses actually, when we are using them to image things, when we are imaging things that consist of several different colors, the images won't look aberrated. And this is actually something that we can easily see with the kind of, for example, mobile phones and single lenses, that the kind of presence of chromatic aberrations becomes more apparent when we are taking images. But by doing things properly, using lens doublets and triplets, so essentially putting many lenses together, we can, for example, already minimize chromatic aberrations. And this is done quite a bit in optics and photonics. But this, of course, we will be saying that this is beyond our course, and will be treated fully in the optical systems and beam propagation course, and that'll be a good one. So we are really focusing more on the kind of aberration corrections beyond paraxial approximation. And another case of a course that we have in our curriculum would be optical design, where we are using ray tracing software, for example, to design different kind of lens systems. So then we are really going fully solving the rigorously the system. So we are not playing and being cursed with the paraxial approximation anymore, but we can really use ray tracing software to kind of design things. And that's quite neat because then you get a better handle of how we can actually do things properly and some in a way that we can really use in real life setting. And as I mentioned, we can take use of different kind of glasses, and there especially it's the refractive index profile of the glasses that matters. So what is the refractive index at a given wavelength and how it changes when we are changing the wavelength. There's also a course on optical glasses, and that would be the name of photonic materials in our curriculum. And there we will be looking at the kind of different kind of optical glasses and how they, for example, affect to their refractive index profiles, especially in terms of their dispersion. So how they change when we are changing the incident wavelength. So this is actually quite important when we are designing things. And now, finally, the final slide, I will be saying that even though we are now relying on paraxial approximation and actually calculating things using the lens equation, please remember that in real life, we are not able to use paraxial approximation, and that's not valid, strictly speaking. So rather, we are using specific ray tracing software to understand how the lenses are working in reality, especially when we are looking at several lenses. So some examples of that kind of ray tracing software would be, for example, Zemax. That's a bit pricey, but it's very good, and you can do everything with that. Another one, which is, I think, a lot more cheaper, if not free, would be Optalix. At least I think there is a kind of free version of that, if I'm not mistaken, that you can use to understand really fully what happens. So basically there, physically, well, of course, you can do also ray tracing that includes diffraction, but you can do geometrical optics ray tracing, and there the main point would be that when we are considering refraction, we are not approximating the signs of those angles to be small, but rather we are just taking use of the Snell's law to actually calculate how the ray of light will be refracting at a given surface. So that's what is done properly using ray tracing software. Each ray at a time will be actually really propagated through the lens system, And at each of those interfaces, we're really properly taking into account how the light is being refracted because of the Snell's law. And when we would be moving away also from thin lenses, so we would be we would be considering thick lenses, then what would happen is that these concepts we have defined, so that the front and back focal lengths, we should be also redefine them. Thick lenses will be considered at the course of optical systems and beam propagation, and lens systems also, and then especially more at the course on optical design. So basically, maybe this figure tells you what happens, that now we would be considering, for example, proper ray tracing. Here we should be considering how the ray will be refracted, and then again at the second interface of the first lens, how ray will be refracted. So we're not only relying on the principal planes of the lenses anymore, and then we would be propagating through a piece of a medium, then into another interface, then refraction again, and so forth. And then at the end, we would have a ray hitting the optical plane at the back focal plane, Fi here. And this is what we would need to redefine when we are using a thick lens or a lens system. And similarly, the front focal length, FFL, and the front focal plane, FO, would need to be redefined. So then we would need to be looking at the rays that at the end of going through the system will be propagating along the optical axis. And then we must kind of backtrace them from which point they are originating at the optical axis, so that this condition will be valid, so that at the end an image will be formed at the infinity. And similarly here we consider a fact that we have an object point, for example, at infinity, so that the ray of light is propagating parallel to the optical axis, and then we're interested in calculating what will be the location at which the ray of light will be coinciding with the optical axis. So that kind of changes will be done into the mathematical formulation, so that the basically back focal length, BFL, would be then the distance between the last lens and the focal point, so that it would be a parameter that we could more easily actually measure in a realistic setting. And then the front focal length, FFL, would be then the distance between the first lens and the focal point. So these were just some considerations for you to kind of grasp that instead of this course, the reality is not as clean and nice, but nevertheless, the physics is quite trivial in that respect. It's just that we need in practice computers to do the computations and ray tracing to understand how the rays of light actually are propagating. Because we should really look at all of those interfaces one by one. And when we start having many of those interfaces, then we should also calculate, for example, how much of light will be transmitted and how much will be lost, because the Fresnel reflection coefficients and transmission coefficients, of course, they are neither unity, so that the more and more we have lenses, then more and more we also start having reflection losses, and less light actually will be forming our image here. And this is incidentally something that starts to be a huge matter when we are using several lenses. And that's why anti-reflection coatings are a very important thing. So thin films and thin film coatings are very important in optics. And incidentally, that's why we also have a course focusing on thin films, because they are essentially used everywhere in optical instrumentation and components to kind of reduce losses. So basically ensure that light will be transmitted through the surfaces we want light to be transmitted. But this was just some mumbling of mine to kind of point you towards the right directions, that how these things will be generalized. So this was now my lecture on combination of lenses. And now that we understand how a combination of lenses will work out, we can next start considering what we can do if we start putting something else between the lenses. So what we can do if you start putting apertures, for example, in our optical imaging system, and what they do or what we can do with them for the image formation process. But that, of course, will be the topic of the next lecture. So I thank you for your time and patience, and please enjoy the morning, your evening, your night, your day, and please join me shortly listening for the next lecture. Thanks, and bye-bye.